Hello everybody and welcome to this SimScale webinar. My name is David Shaw. I am the product manager for structural analysis here at SimScale. And today I'm really excited because I get to show you what we have been working hard on in terms of vibration simulation. So without further ado, let's get into it. We're going to give you a quick introduction to SimScale for those of you who don't know us. I know we've got a lot of customers here, but we've got a lot of also prospective customers. A few students and yeah, so I'm from all over the world as well, so that's great to see. I'll give you an introduction to SimScale and then into the new features. So I'll give you a bit of an introduction to the theory as well as a live demonstration of those features. So SimScale, what do? We are all about empowering engineers to innovate faster. And how do we do that? We make high fidelity engineering simulation truly accessible and at any scale. Okay, so we are a cloud native simulation platform. And I'm going to show you now how my part of the product, so I do structural analysis, that's one part of SimScale. I'm now going to explain how we actually make high fidelity structural analysis truly accessible. So in terms of advanced structural analysis, what I'm talking about are things like vibration analysis, nonlinear static or nonlinear dynamic analysis, thermomechanical analysis, these slightly more advanced structural analyses that typically are inaccessible to the broader engineering community, right? Yes, the simulation expert departments will have access to all of these tools, but what we're doing at SimScale is making these kind of analyses accessible to all engineers within an organization. Now, the other part is that those analyses are the ones that get a massive boost out of being cloud driven. Okay, so it's really comes with both. Our product is going to give you the advantage of making it accessible, but also you'll get the supercharging effect of cloud simulation, which is really felt most strongly for these more advanced analysis types. So how do we make advanced structural analysis truly accessible? We do that by, number one, being cloud native. That means you can access at any time from anywhere and at any scale. Okay, it's not a remote desktop. It is purely built in the cloud. It's true software as a service, and yeah. So once we get into platform, you'll start to understand all about that. We are truly scalable. Okay, so that means that there's no limit on the number of simulations that you could be running in parallel. And when it comes to vibration analysis, the topic of today, you'll also see that that can be a massive advantage where vibration analysis, you need to do it in multiple directions. You need to do it at different damping levels, and you can run all of that in parallel with the SimScale platform. We are one platform with a unified experience across a broad spectrum of physics. Okay, so yes, there's my colleagues who do the flow analysis, electromagnetics. I'm responsible for structural analysis, and within structural we have a broad range of physics, so going from basic static analysis up to nonlinear dynamic analysis, heat transfer, and frequency domain analyses as well. This is catering for different types of users as well. So we try to really make our workflows as easy to use as possible with lots of automation that will enable those users without much simulation expertise. But we also allow the customization and the advanced settings for the simulation expert users. Okay, so it's a platform that really tailors to different user groups, because simulation it comes into different points in the design cycle, and it comes into different departments and different users. Okay, so we're catering for that spectrum. Another part of doing that and making it accessible is providing the best-in-class support. So I can really testify to this. I've worked in the simulation industry for a long time, and there's really nothing like SimScale support. And that's primarily because we are cloud-based. It means we can, just like we run our simulations in parallel, we can also support our customers in parallel. Because there's no data transfer, we're able to immediately help out our customers when they're experiencing the problem. So if you have questions, if you need a simulation engineer to jump into your project and help you along, then we're there to help when you're experiencing the problem, right? So that was my old job, and I can really testify that it was it's not like what I was doing at previous more traditional simulation companies. We're also cost effective, okay? So we can scale in terms of licenses to a huge number of licenses for a company very, very flexibly, okay? So those are my 5 key points as to how we make advanced structural analysis truly accessible. Now, in terms of the value that you get out of accessible simulation, and we're going to focus on vibration simulation in this webinar because this is where we've been doing a lot of development work. So what is the value of doing vibration analysis? So we at SimScale, we believe that simulation should be used at all stages of design, and as early as possible is where you're going to benefit the most from design insights. Okay, so when you're using vibration analysis during your product development and design, you can do 2 main things, both getting design insights before you move on to physical prototyping, which allows you to disqualify poor concepts up front. It allows you, in the case of vibration analysis, it allows you to identify the risk of resonance very early on, maximize the low energy modes. Okay, so we move those very dangerous modes outside of operating ranges, like you can see over here on the right hand side with my electric motor bracket, that I've done some parametric optimization here, changing the design to stiffen the part to move the first eigenmode away from the shaft, from the electric motor operating frequency. Okay, so doing that early stage avoids the actual resonance happening in the physical prototyping. Okay, the same goes for noise as well. Noise and vibration are implicitly interlinked. The second thing that we gain value out of simulation with is that we can replicate the physical tests themselves. So we can understand what is the structural risk. We can say, is my product going to fail this physical test before we actually take it to the testing facility, spend 10K on a single test regime. We can already predefine if we've got a good design candidate before we get to physical testing. Okay, if there is a problem, if it is going to fail, we can see where that failure occurs and why it occurs. So in a physical test, you have a few accelerometers, a few strain gauges, but you don't get the point-wise detail that you need to understand why a product fails and how we might be able to mitigate that with different design iterations. Okay, so those are some key points as to why we want to do simulation during the process. And to be honest, the majority of vibration products, they need to be certified under international standards. Okay, so we replicating those standardized physical tests, it brings a lot of value if we do that as early as possible. Now we see this at SimScale with a number of products. So that's batteries and fuel cells. So in the electrification industry, we see a lot of use cases of vibration. Inverters, we'll have a look at an inverter today, but also in the AC world. So heat pumps, very vibration sensitive, and there's of course general mechanical systems, for example in automotive, control arms, different hydraulic systems, different piping systems. We have a lot of customers who need to investigate vibration performance for those kind of products. So that was enough of general background. Let's get into what we have recently released. So the main change that we've made for our vibration analysis, or additional feature for our vibration analysis, is a method called the modal-based harmonic analysis. So this really allows us to supercharge vibration analysis, capture many excitation frequencies in a single analysis, and it's very efficient for larger meshes. Now, what it is a combination of modal analysis, frequency analysis, and harmonic analysis. And I'll go into a little bit of detail about the differences between modal-based harmonic analysis and what we have traditionally been doing is direct harmonic analysis. We'll look at that on the next slide as well. Okay, so number one, we've got a new method for harmonic analysis, allowing us to be super efficient with large meshes. And it also allows us to automatically capture the resonant response. So because we're coupling the two analyses together, we actually know where resonance is going to happen, which means we can focus our attention in the harmonic analysis around those dangerous modes and really understand what is the level of resonance and the stresses at those peak points. And we'll see that all in action in the platform. We've got two new options for that. Number one, we cluster our harmonic excitation frequencies around each mode, right? So then you'll get very accurate resolution of the modal peaks. And we've got another option called cover spectrum, which does the modal peaks, but also resolves the full spectrum in the troughs as well. So you can see that on the plot in the left-hand side. I've used the cover spectrum option here. You see it nicely resolves the spectral peaks, the modes here, but it also resolves the space in between as well. So we get a really good high fidelity full spectrum response. Thirdly, we have enabled global damping. Now, this is really to make a user-friendly method for applying damping in the system. So with global damping, you can apply a constant level of damping to the full assembly as a percentage of critical damping. We'll see this in action in a minute, but it just makes, rather than doing material-based damping, it just makes for a much easier, and particularly when we're in early stage design, the ability to apply damping in a much more user-friendly manner. So the difference between modal-based harmonic analysis and direct harmonic analysis, essentially, we're solving the problem on a different basis. So with direct harmonic analysis, we solve the vibration study using the nodal degrees of freedom, so the X, Y, Z displacements of each node in the model. Now, for a large mesh, this becomes a very large number of degrees of freedom, which means it can be very computationally intensive to solve, and particularly to save many excitation frequencies. On the other hand, modal-based analysis, rather than using the nodal degrees of freedom to describe the dynamic response, the dynamic response can actually be described as a combination of the eigenmodes and the eigenfrequencies of the model. Okay, so this is great because it allows us to, even for a large mesh size, a very complex model, it allows us to be very efficient once we have done the modal analysis. Okay, so we only need to run the modal analysis once, and then we can do harmonic analysis based on those mode shapes. So this makes it efficient and accurate for low frequency system vibration. So when we're thinking about base excitation, and we're thinking about, for example, road induced vibrations, we're going up to sort of 500 hertz or so, fairly low frequency, which is where then modal based analysis really comes into its own to have an efficient method for capturing all of the dynamic response and the low frequency range. It also enables us to automatically capture the resonant response, as I mentioned in the previous slide, and fully resolve the full spectrum. It also comes with a few additional options for damping, so we can do modal damping rather than Rayleigh damping, or we can do both actually. So in terms of bringing in different damping methods, then direct and modal will have different options. Now, a direct method, it still has its purpose, okay? So it's very accurate, but it is resource intensive. It's decoupled from the modal analysis, but you should still really run your modal analysis to make sure you know where to focus your harmonic analysis. And then we would use it still in cases of local high frequency vibration. So maybe a single frequency assessment of a very high frequency local vibration. Okay, that is still somewhere that it's going to be hard to get an accurate result with the modal based method. Okay, so hopefully that wasn't too boring in terms of the differences in methods that we have on the platform, I'd now like to really jump in to an example, and I'll then give you a full live demonstration of the new capabilities in action. So we'll look at an EV inverter. So the vibration assessment needs to be, so the product needs to be designed to withstand 8G sinusoidal vibration up to 80 hertz. So this is typically stipulated in, for example, the UN testing standards, and it's based on road-induced vibration. We will also need to make sure we assess the vibration performance in 3 perpendicular directions. So if you're a test engineer, if you're a vibration test engineer, you need to be testing your model in multi-axis shaker table testing. We can replicate exactly the same thing in SimScale, and because we can run in parallel, that makes us very, very efficient in those cases. In terms of damping, we want to be reporting our vibration response at a worst case level and a best case level. So we're going to look at 2% damping and 4% damping. Now, the reason we do that is because damping is a very difficult research subject. So to actually get an accurate damping value for different materials, and also different materials that have been combined with welding, with different joints, the damping behavior is going to depend on all of that, the internal frictions in the model, as well as the internal friction in the materials themselves. So it's very, very hard to get an accurate indication of the true damping level in your system. So best case or best practice for FEA is actually to report at different levels of damping. So one worst case and one best case scenario. So before we get into the platform, I'll just show you a couple of the design insights that you get out of a simulation like this. So the first thing I would do when I run a vibration analysis across my full range, across 500 hertz, is to go through the results and see where do we have resonant behavior. So I've scanned through the different, I've scanned through the frequency range, and I can see that I have 2 parts that are being excited, that are being excited at certain frequencies. So we can see the coil here. We have a coil in the inverter, and that seems to resonate particularly when we get up to here at the 180 hertz or so. We also see that the connector piece on the back here, that also starts to resonate at about 408 hertz. So this is the beauty of modal-based analysis. With a single simulation, you can already see or automatically capture the resonant responses just with a single simulation. So we can see the coil and the connector are of particular interest. So then I've put some point data, one on the coil and one on the connector in red, and we can then see the peak displacements during this analysis. Okay. You can then dig down into each frequency. So let's take a look at the coil first. We can see the actual vibrating motion, as well as the stresses induced in the model. Okay, so then we can start to really understand, hey, is this maximum vibration amplitude, is that going to cause clearance issues? So is there going to be rattling? Is there going to be noise? And is this part likely to break because of the high stresses in the model? Okay, so we're starting to get up to some pretty high stresses here. So in this case, we may need to consider design changes, but already having this information up front allows us to really understand where is the risk, the vibration risk in our product. Same for the connector. We can visualize the vibration itself, and then we can look at the stresses induced as well. So the vibration on the connector is really not very much at all, and low stresses as well. So not of concern. The coil does look a little bit dodgy. So if I was designing this inverter, I would potentially be looking at strengthening up that coil and trying to reduce the level of vibration in the system. This was the best case scenario, so I did 4% damping. Now what I'd like to do is a complete live demonstration of the platform. Okay, so let's bring SimScale into the picture. There it is. So SimScale, as you can see, is completely browser-based. It's contained in I'm using Google Chrome here, but you can use any browser that you wish. And that means I can access it at any time from anywhere. And because the simulations themselves, they don't run on my local hardware, they run on a cloud instance. That means it can be accessed at any scale. So you can bring in a small model, it's going to use a small mesh. Bring in a large model, it's going to require a large mesh and run on a large machine with the RAM requirements for that problem. So I've already done one vibration analysis. I've done the best case scenario here, so the 8G at 4% damping. But let me take you through step by step how the vibration process looks. So if you bring in your geometry, I've brought that in as a Parasolid file. You can bring it in as native CAD from SolidWorks, from Autodesk Inventor, from Creo, from CATIA, wherever you like. So we can handle all of the CAD file types. Bring that in solid body CAD, and you create your simulation. So from the simulation library, you can see all of the different analyses that we have. And again, one platform with broad physics. So you can have CFD analyses, electromagnetic analyses, and structural analyses all in the same project. I'm running a harmonic analysis here. So I create my harmonic analysis. It's automatically found the contacts themselves, okay, between the parts. It's bonding them together, but you can go in and you can change them to sliding, or you can adapt the surfaces and manually manipulate them. I will turn this on. So this is a new feature that we're working on, which is called allow node merging. So for these bonded contacts, what we're actually going to do when we toggle this on is, rather than using a linear relation between from one side to the other side of the contact, we're actually, during the meshing phase, we're going to merge those nodes together so that we, number one, reduce the node or the overall mesh count in our simulation, and also improve the accuracy. Okay, so when you've got shared nodes on contacts, you're going to have perfect heat transfer, perfect mechanical connection as well. So this is a great feature for having an efficient simulation. I'm then going through, and under global physics, I can then add the new global damping option. So I enable global damping. The best case scenario was the 4%, but we're going to run the 2%, the 2% critical damping situation for this one. Now let's go and create some materials. So you can bring them in from the default library. You can create your own materials, or have your company material libraries also created on the platform as well. I am going to use aluminium first, and I've created some sets of the different parts here, just so that we're not going to be doing too much clicking whilst I'm demoing here. We're going to create the copper material, apply it to the copper pieces. Just change the visualization here a little bit so we can see everything. So we've got the capacitors, the coils, the copper wiring. You're using copper for those components. For the PCB board, we'll use an FR4. And we'll use some polypropylene for some of those plastic components. And finally, for the transistors, we're going to use a silicon. Now we're only caring about the mechanical properties here, right? Not the electromagnetic properties at this stage. So we've got our materials set up. We can now create some boundary conditions. So we want to do a base excitation, but for a base excitation, we first need to define where are we going to fix this model. Okay, where are we going to fix it to our shaker table to be excited? So we're going to use a fixed support, and I'm going to go in all of these bolt holes here. So we're going to fix it at all of those locations, and then we're going to apply a base excitation. So the base excitation drives an acceleration at those fixed supports, right? So you can imagine it being clamped into the shaker table and then shaken from those supports. So let's start with the X direction, and we need 8 times the gravitational acceleration. So we're going 8g. And that's it for the actual for the boundary condition setup. Nothing fancy there. Numerics. So our solution method at the moment is at direct. That's our traditional method, but you can switch to the modal-based method, which is on our new development. Soon we'll make that the default as well, because it really does suit our customer base better than the direct method for general design usage. So we'll hit save. And under simulation control, this is also where we've added a lot more features for automatically capturing that resonant behavior. So first, what I want to do is enable one of these new features. We'll use the cover spectrum, right? So we're going to fully resolve the entire spectrum around the modal peaks and within the gaps between them as well. So we want to go up to 500 hertz. Now, an important part, or the most critical part of a modal-based harmonic analysis is to ensure that your modal base is sufficient to actually define or describe the dynamic response accurately. Now, as a rule of thumb, you want to use a modal base that includes all the modes up to twice the maximum loading frequency. So we have an automatic option for that, where you can say apply, do the modal analysis up to, in this case, 1000 hertz. Okay, so our end frequency in the harmonic analysis is 500 hertz, but we're going to use a modal base that goes up to 1000 hertz, just to make sure that we are including those modes that are going to be important for the lower frequency range. That's a good starting point. That's a good rule of thumb to get started. But if you want full-blown accuracy, once you get to validation, the validation side of things, I'll show you this in a minute. You can also say, you give me a frequency range and pump it up to 5,000, right? And try and make sure you include all of the modes of importance. And you can tell that using something called modal effective mass. We'll get into that in a minute. But for now, we'll use our general rule of thumb, which is use a modal base that is solved in a frequency range twice the size of the harmonic analysis. Okay, so we've got our simulation control all set. The machine size is going to be selected by SimScale using our machine learning, but you can also manually select which size machine you want to use for the specific simulation run. Now, in terms of meshing, we can use fully automatic meshing with tetrahedral elements. We also have manual refinement options for creating prismatic or hexahedral elements for doing surface-based refinement and so on. But for early stage design here, we're just going to go with second order tetrahedral elements for capturing the geometry fairly coarsely to begin with, and then you can work progressively from there. So I've already got a mesh here. So that took 10 minutes to create the mesh, and mesh size of 336,000 nodes or so. So that would be pretty heavy for direct analysis if we wanted to output many frequencies. For modal based, that's no problem at all. So now I can create my first simulation, and we're going to say 8G in X, 2% damp. There we go. And now you'll start to see SimScale really in action. We'll go back to our boundary conditions. We change to the Y direction, and then we can set up another simulation. I'm just going to copy the name here. Set up another simulation in parallel. 8G in Y, 2% damp. Okay, so those two simulations have gone off into the cloud. There's no queuing here. They're going to be run in parallel on separate machines. We'll do the next one. And same again. 8G in Z, 2% damp. So then what we're essentially doing here is replicating multi-axis shaker table testing, and we're able to run all of those simulations in parallel. Now I could keep going. I could go and change my global damping to 4% and run the best case scenario at the same time. I won't do that because I've already run that up here. But hopefully that gives you an impression of really what we're doing here with SimScale, making these slightly more advanced simulations both accessible and boosted by cloud computing. So if we go back to the one I did earlier, you can see the simulations that I've already run here. So we've got the I actually started with a 30G. I wanted to see if we could really break this thing, and yeah, 30G is not good for the coil, so that thing nearly flies away. And yeah, so I did it with the 4%, just with our twice. If we go back to simulation control, twice the maximum loading frequency as our eigenfrequency scope. Okay, so that's our good rule of thumb, and that's going to be decent at capturing the resonant behavior between 1 and 500 hertz. But if we want to be 100% accurate or go to sort of validation mode, what we can do instead is pump it up. What did I use here? I used a frequency range going up to 5,000 hertz, and there we managed to get, in our modal plots, we look at the accumulated modal effective mass. We see that the accumulated modal effective mass in every direction went above 85%. Okay, so when we want fully accurate modal-based harmonic analysis, we want to make sure that our that we're using all the modes that will contribute to the dynamic response. And the way of telling that is to make sure that you capture up to 80% is the rule of thumb, 80% modal effective mass, and then our modal base is going to be sufficient for capturing all of the detail, all of the dynamic response. Okay, so you can run in two modes, sort of first early stage design, but also pump it up to the full validation stage as well. Now, as those simulations run, we can have a look at some results. So if we look into the post-processing, once the simulations have completed, you can scan through the different frequencies. Let's look at the coil again. Somewhere around here. And we can visualize both the deformation and we can have a look at von Mises stress as well. So we've developed a max over phase von Mises stress. Right, so von Mises stress is a little bit tricky because it uses many components, or all of the Cauchy stress components, right? But each of those Cauchy stress components in our harmonic analysis might have a different phase angle. Okay, so when we compute von Mises stress, then we actually have to do some clever calculations behind the scenes to ensure that we're using the correct phase for each component within our von Mises stress. Okay, and that's the max over phase von Mises stress that we've developed here, and that gives you a very nice, easy way to look at peak stresses within your model. So let's quickly animate that for there we go. Okay, so that brings my live demonstration to a close. What I will do now is head back to the slides, and I can open for a few questions if there are any. But yeah, as I say, we've been really focusing on vibration analysis because it's something that is really one can replicate vibration assessment very, very easily. So it really lends itself to this approach of SimScale of making more advanced structural analysis accessible to everyone. Okay, so when you know you need to do, for example, UN 38.3 vibration test, it's always going to be the same. So with SimScale, you can already have your simulation template set up like that, and then use that for new projects further down the line. And because it's all cloud-based, you can share these templates between departments. You can collaborate directly in the SimScale platform as well, both within your organization and with the SimScale support team as well. So that was a lot of information. I will ask now if we have any questions. I know we've run a little bit over time, but yeah, it'd be great to hear from the audience here. So I can see we have a few. We have a few questions coming in already. So I'll answer these questions. But yeah, if you're not sticking around for the Q&A, then please, in terms of next steps, give us an email, either to myself or to the sales department, and we'll have an application engineer get in touch with you as soon as possible. So we have some questions about the recording being shared. Yes, of course, we're going to be recording the demonstrations, and we'll send that out to everybody. Now, the interesting question from Alberto: can you apply random vibrations that you define in terms of acceleration PSD? Great question. Not yet, but this is the next step for SimScale vibration. So we've now got our modal-based analysis, and then on top of that, we can build random vibration. Okay, so that's going to be our next step, doing a random vibration application where, rather than applying sinusoidal vibration, for example, like we've done here at 8G or at varying amplitudes, we can also go into we'll be able to upload PSDs or create your own PSDs, power spectral densities, for the vibration on the platform to run the random vibration analysis, and from that you'll then get your root mean square stresses and displacements, velocities, and so on. Okay, so that's coming next. So stay tuned for random vibration, which is just around the corner. So yeah, great question. In terms of in other simulation tools, this feature is described as mode superposition. From Tobias, absolutely, yes, it is, and this is exactly the same. So it's got a number of different nomenclatures, but we're calling it modal-based analysis. But it's exactly the same as what you would be used to in SolidWorks or in ANSYS. What we're doing differently is offering both direct and mode, and the ability to run it all in parallel as well. So there's a few other ones. I'll take the other ones via email because they're more about administration and sales reach outs. And yeah, I think we'll leave it there for today. So thank you so much for attending, for listening, and yeah, I hope to hear from you, and or the sales team will hear from you. But yeah, if you want to discuss theory or what you see would be a good fit for SimScale, that's really what I want to hear about. Okay, so do reach out if you have any questions or comments, and I'd love to hear from you. But until then, thank you very much for listening, and have a great day. Okay, thank you very much.